Hello learners, let's study motion, a simple phenomena that we experience daily. Do you know that everything in the universe is always moving? Even if you are completely still, you are still moving. How is that possible? Well, it's not hard to think of that. It always happens when you drive a car. Even if you are not driving any car and are completely sitting still, you are still moving because the Earth, the planet on which you stand, is continuously moving around its axis and around the Sun. In this chapter, we will not only cover the basics of motion, but also cover many NCERT exercises and past year questions so as to give you knowledge and make you fully prepared for your examinations also. So, let's start. Here's what motion actually means. Motion means a change in the position of an object with respect to time and relative to an observer. So let's decode the first part of a definition, that is, change in position of an object with respect to time. So if an object is at point A at t is equal to 1 and it reaches to point B at t is equal to 2 seconds, then we say that the object has moved or motion has occurred for the object from point A to B. Now let's decode the second part of the definition, that is relative to an observer. What does this mean? Say for example, you are driving a car at 80 miles an hour and behind is your friend in his car at 60 miles an hour. Now if you look in the rear view mirror, as long as you both keep your speeds constant, you will notice that your position does not change with respect to each other. Or you can say that you will always be at the same length from each other. But does this mean there is no motion? Well, of course, both of you are moving, but only when you measure your position with a fixed surrounding, such like the fence that we can see here in this animation, you can say that you both are moving. Thus, motion is always relative to an observer. So any object can have two states. Number one, the state of rest, which means the object do not change its position with respect to time. Time here is important. Also, the second one is the state of motion, which means the object changes its position with respect to time. So this was a brief intro about the motion. Let's move on to our first main concept of this chapter, that is distance and displacement. Let's understand this with an example of a car trip. Say you are driving a car. You are at point A and you want to go to point B. You will see the distance you can travel is along the blue line. Hence, the blue line here shows the distance you will travel from A to B. But say you want to find the shortest distance, that will be the black line, or you can say displacement. So can you define them now? Let's see. Distance is the total length of the actual path that a body travels, while displacement is the shortest distance covered by the body between its initial and final position. These initial and final position terms are important here. Secondly, distance is a scalar quantity. What is a scalar quantity? A scalar quantity is one which has a magnitude, a value only. And displacement is a vector quantity. Now what is this vector quantity? Vector quantity is the one which has magnitude, a value, as well as a direction associated with it. So if you say 20 kilometer, that is distance. And if you say 20 kilometer due east, that will be your displacement, because we have mentioned a direction here. Now both these terms can sometimes be equal to each other or vary from each other. How? Let's see. So if you check this path 1, if you want to go from point A to point B, then the distance of the path will be equal to the displacement, because it is the shortest path between both the sides, that is a straight line. But if you check the path 2, if your distance is your black line, then your displacement would still be the same path as in path 1. That is displacement, because displacement is the shortest path available. So in the first case we saw that the distance was equal to displacement, and in the second part the distance was greater than the displacement. The displacement can never be greater than the distance because it is the shortest distance covered by the body. Now another interesting thing to note is that distance can never be negative because it is the actual length, and length cannot be negative. Whereas displacement, it can be negative. How? Let's see. So say if a body starts from point 0 and goes to point 5 in this direction, then we say the displacement is 5 units. But if the body starts from 0 and goes to minus 5 in this direction, then we will say the displacement is minus 5 units. Because here displacement is dependent on direction. If we go into the negative direction, the displacement will also be negative. I hope this is clear. So now we move on to our next concept, that is speed and velocity. So again, let's go back to our car drift. While driving a car, if the car runs at 25 meters per second, you check your speedometer and it says 25, right? But if you change your direction, if you go in the opposite direction, but keep your car speed constant at 25 meters per second, then you will not notice any change in your speedometer because your speed is still 25 meters per second. But your velocity, which just like displacement is dependent on your direction, it will change to negative 25 meters per second. So let's define these two now. Speed is the distance covered per unit time. So speed is equal to distance s divided by t. Whereas velocity is equal to the total displacement covered per unit time. So velocity is equal to d displacement by time t. So speed is also a scalar quantity, which means it has a magnitude only. Whereas velocity, since it is dependent on a displacement, which in itself is a vector quantity, that means velocity is a vector quantity as well. Just like we saw here, it has magnitude and direction both. So again, just like we saw in the example, the speed remains the same even when we change our direction, so it cannot be negative. And velocity, when we changed our direction, was negative. So velocity can be negative. But the speed that our speedometer shows here, it's the instantaneous speed. That means the speed at that particular instant only. What if we want to calculate the speed for the whole trip from one point to the other? Let's see how we do that. So for that purpose, we define the term average speed and average velocity. So average speed by definition is the total distance covered upon total time. So if a body travels from point A to point B, which are at a distance of 5 meters, and it takes a time total of 2 seconds to reach from A to B, then the average speed will be 5 by 2 meters per second. Similarly, we can define the average velocity as the total displacement upon total time. There is also another formula for the average velocity. Say the body travels with the velocity v1 for a certain period of time and a velocity v2 for another period of time. Then if you take the average of these two, that is the sum of both divided by the number, that is 2, you can also calculate this as average velocity. So we can also define average velocity as the sum of velocities divided by the number of velocities. So I hope this is clear, and we now head on to our next topic, which is Acceleration. So by definition, acceleration is the change of velocity with respect to time. So if a car changes its velocity, that means it speeds up from velocity u to velocity v in time t. Then we say the car has an acceleration a, that is the final velocity, minus the initial velocity, which gives us the change in the velocity, divided by the total time in which the change occurs. And since it deals with a velocity which is also a vector quantity, we use these arrows to represent a vector quantity. That means acceleration is also a vector quantity. And since it is a vector quantity, it can be negative, and negative acceleration is called retardation. Clear? So having studied the basic terminologies of our chapter, let's use them to study the motion graphically. So we can use the graphs to analyze different types of motion. We have a position time graph or the xt graph, or we also call it the distance time graph or the st graph. Then we have the velocity time graph. Then we have the velocity time graph or the vt graph. And we also have the acceleration time graph or the at graph. But basics first. While plotting the graph, we take the independent variable, that is time, as along the x-axis. And we take the independent variable, which might be displacement or velocity or acceleration, across the y-axis. So without wasting any time, let's now analyze the different types of motion using these graphs. So first we have to analyze the state of rest. So what does rest mean? Rest was when an object is not moving at all. If its position does not change with respect to time, that was rest, right? So in the position time graph, you can see here that object does not change its position as the time progresses. See, its position is constant. So this is the position time or the xt graph of an object at state of rest. For the velocity time graph, we can see that the velocity is 0. Why so? Because there is no change in position, and velocity is the change in position per unit time. So here velocity is 0, and hence the vt graph shows that the velocity does not change, rather it is 0 as the time progresses. And since acceleration is also 0 here, since it is dependent on velocity, which is again 0, acceleration is also 0 here. And this is the acceleration time graph of the object at a state of rest. See, so simple it is. So that was the state of rest. Now we come to the state of motion. And under that, we will first study the graphs for the uniform motion. So what is uniform motion? Uniform motion is the one in which the object moves with a constant speed or a constant velocity. So as you can see here, if you check the vt time graph, the velocity does not change with respect to time. So this kind of motion is uniform motion. So if we talk about the distance time graph here, we will see that since it is a constant speed, that means the change in distance or the change in position will also be constant. Thus, we can see we have a straight line. So if you are at distance 1 at time is equal to t is equal to 1, then at time is t is equal to 2, you move to distance 2. Thus it follows that at time equal to 3, you will be at distance 3 meter. So this is our distance time graph, which is a straight line which represents none other than the velocity of a motion. And again, if we check the acceleration time graph, then since the speed is constant or the velocity is constant, there is no change in velocity. Change in velocity, this triangle shows the change in a value of something. So the change in velocity is equal to 0. That means our acceleration, which is change of velocity per unit time, is also zero, and as it can be shown here, and as it is shown here. So that was uniform motion, and now we go on to the non-uniform motion, or we can say accelerated motion. So first we will study the constant acceleration motion. So if you have a body which is at point A and it speeds up to reach point B with an acceleration A, then this represents accelerated motion with a constant acceleration A. So say this is a car and you hit the accelerator. What do you think will happen? Yes, the velocity of the car will increase. The velocity of the car will increase. So, if we check the velocity time graph, if at time t is equal to 1, we have velocity 5 meter per second, then at time t is equal to 5, we will have 15 meter per second. See, our velocity increased since it is accelerated motion. The AT graph shows us that we have a constant acceleration for a duration of the motion. But for the position time graph of such motion, take an example like this, that at t is equal to 1, if you are at position 3 meter, then at time t is equal to 2, since your velocity has increased, you will be at a position, let's say 5 meter, and then at time t is equal to 3, you will be at a position much greater than that. So you're at 10 meter. So as you saw here, with the subsequent time interval of fixed duration of 1 second, your distance or your position did not increase constantly. First, your position change was 2 meter, and then in the next subsequent second, your position change was 5 meter. So that is what we call an accelerated motion. So this is the XT graph of a constantly accelerated motion, and for such type of a, see, it is a curve, and for such type of a curve, we call it a parabola. And another interesting thing that you can take out from here is that if you, in the VT graph, if you take the area of the graph, that is this trapezium, then this will give you the total distance covered. So in our case, you can see that the total area under this curve will be the area of the trapezium, that is half times the sum of the parallel sides, that is 5 plus 15, multiply by the total time, that is 5 minus 1. So in this case, our total distance traveled will be 40 meters. So the area under the VT graph gives us the total distance traveled. But you do not always accelerate the car, right? You also apply the brakes when you need to. What happens then? So when you apply the brakes, you are providing a negative acceleration to the car, and that is called retardation. Remember? So here we can see when we apply the brakes, what happens? The car slows down, right? So here also we can see in the VT graph that the velocity of the car slows or lowers down to 0. Here we can, by the AT graph, it is shown that the acceleration has a negative value because we are applying the brakes. But shouldn't the position time graph also be negative? No, it will not be, because as we see here, we still have some positive velocity, which is although decreasing after every time second, but still it is a positive value. That means our change in position will be positive. Thus we can see here, although the position of a car increases as the time goes on, but the increase is not much. Say for the first instance, you are at position 3 meter. In the next one, you are at 5. Then since the velocity is decreasing, in the next interval, you might only go to the 6 meter. See, the difference here was 2 meter, and here the difference is only 1 meter, although it has increased. So that's our position time graph for constant retardation. And we can see here that when velocity reaches to 0, our position again attains a constant value, just like we saw in the state of rest. So I hope now you have got a gist of all the topics we have studied so far. We first revised what is motion, then we discussed two terms, that is distance and displacement, out of which displacement we learned was a vector quantity and distance is a scalar quantity. Then we also learned the term speed and velocity, out of which again velocity, since it is a vector quantity just like displacement. Then we learned about acceleration, again a vector quantity, and then we went on to analyze different graphs of the motion, out of which we learned the xt graph, the vt graph, and the at graph of various types of motion, as well as the state of rest. So that was all from this video. We will be back with another video in which we will discuss the NCERT questions based on the topics so far we have discussed in this video, so that you can consolidate all we learned and use them in your exams as well. Thank you.